Alright, so this is EM2, and so I have already set up the machine. So what you'll see is we have our magnitude of impedance there, and it is also set for the Y scale to be in logarithmic. You can see that by just how the spacing of the lines are. And so what we're going to do is we are going to start with our 470 ceramic capacitor. So we have two. We have our 470, which is our larger one, and then our 47 picofarad. So we'll start with this one. Now this might be a little bit difficult for me to record, but essentially I'm going to pause real quick. There we go. Okay, so what you'll see is I have connected the 470 ceramic capacitor into our clips, so they are connected between the black and the copper, and this is what we see. And so what we'll want to do is do our auto scale, and that is under our scale ref, auto scale. All right, so now what we have to do is we have to look at the measurements at 1 megahertz and 500 megahertz. And so how we can do that is we can hit marker appears on the screen, and then we will do 100 m for megahertz. Oops, that's wrong. I meant 1 megahertz. All right. So now you can see the marker on screen is at 1 megahertz, and you'll see that we have 1 megahertz, and then we have impedance. Remember, impedance does not equal capacitance. So what we'll write is our magnitude impedance is equal to, that is 1.3656. 3656. All right, remember that is our impedance. There is a formula that you can use using angular frequency, which you can derive from frequency, in order to get that capacitance. That'll be your job to do. So next I will type in first marker to select the marker, and then 500 m for megahertz. And then we get we will do magnitude impedance is equal to 578.73. Now we have this thing called resonant frequency, and so I'm going to explain that real quick. So in an ideal world, because these are non-ideal, right? Because we live in the real world, everything's non-ideal. An ideal capacitor, when you're looking at impedance versus frequency, an ideal capacitor will continue to decrease impedance as frequency increases. However, with a real capacitor, what we see is there's this big dip. So it acts like a capacitor, and then there's a dip, and then it begins to act like an inductor, because an inductor, when you have log Z versus frequency, what you'll see is that there is a rise until the resonant frequency where it's acting like an inductor, and then it'll begin to act like a capacitor. So going back to our example of the capacitor, so what we'll see here is that we're looking for this spot. Now, I could just do the marker and make a bunch of guesses, but one thing I can do is I can use the spin wheel. And the spin wheel will get me all the way over there. And so, might take a little bit of fine tuning. That looks good. All right, so our resonant frequency is 32.468 megahertz. All right, and then I am going to do that again for the other capacitor, and then I'll start up with the next section.